Okay, so we are going to discuss Euler flows. Um in particular, inviscid flows means that the fluid has no viscosity, or rather, we are going to ignore viscous flow effects in the fluid, right? Why are we doing so? Well, right in the first class, I had said, well, one can always solve Navier-Stokes equation, energy, momentum, and mass conservation equations in all its glory, but that often doesn't give rise to insight. So what we're going to do is take a simpler version of the general Navier-Stokes equation of fluid flow, where we make the assumption that fluid viscosity, or the frictional forces between layers of the fluid, because the relative motion is not going to play a role, and see how far we can go with that. The equation can Are there circumstances where the equation becomes much simpler? And if it's simpler, can we understand simple flow profiles using Euler equation, uh, where one neglects the viscous term, and so on and so forth. So the way we're going to go about it is, we're going to first get the Euler equation, understand it and its consequences, and this is going to basically follow David Tong's lectures. But after that, I think it's relevant to ask, why are we studying Euler equation? When can we neglect the viscous terms? When is it valid? And under what circumstances it helps us study uh, a fluid flow system with Euler equation. And for that, we are going to use the book of Physical Hydrodynamics by four authors. And then we're going to also discuss various idealized flow fields. And in a certain case, when you have irrotational flow, one can define a scalar field from which one can take the grad and calculate the velocity field. And so we're going to discuss that and calculate potential functions, velocity potentials, for a set of 4 or 5 simple cases, because by combining these simple cases we can understand more complex flows. And finally, we're going to have a study of flow around spherical and cylindrical obstacles, right? So that's the plan of this lecture and the next two lectures. Where do we start? We start with first reminding you that fluids do have indeed viscosity, and if you have two layers of fluid moving with respect to each other, which means that this layer has velocity v plus dv, suppose, and this layer has a velocity v, such that there is a velocity gradient dv, right? And suppose this is the x direction and this is the y direction. So if the fluid is moving in this direction with respect to the other with a velocity gradient dy, that means you have to give a force in the top layer of the fluid and in the y direction. So hence there is a force per unit area, because if you increase the volume of the fluid, or the area of the fluid which is moving past each other between these two layers, the force has to increase. So force per unit area is eta, the viscosity, into dv, the change in velocity along the x direction. This is the x direction as per the diagram. What is the direction of A? By the way, the force is being applied in this direction. The surface area element is parallel into the plane of the computer, if you like, uh, and thereby the normal to that area is in this direction. This will also become important later when we discuss various stress tensors. So what the viscous terms does is give a friction force between layers of the fluid moving with the velocity difference relative to each other, and this frictional force also leads to dissipation, right? Energy loss. But in today's class, the next, we are going to ignore viscous forces between moving fluid elements and look at what are the consequences. And next class we're going to see, is that even valid? I mean, when can we do it? Of course, for the superfluid we can do it, but are there other cases when we can use Euler's equation and simplify the more complex equation and get an understanding of the fluid flow, right? And also derive the equations and discuss what circumstances we should be studying Euler equation. Okay, so with this, we first discussed the conservation of mass, and you might know that the conservation, because you're in the fourth year, and any conservation equation is written as whatever that quantity you are looking at. Suppose rho is conserved, mass is conserved. So rho is the mass density. The rate of change of mass in a unit volume is equal to divergence of rho u. And why is that true? Well, one can understand this. Uh, One can understand this by suppose having a volume of fluid inside which there is so this surface area is fixed as a function of time. Okay, so it's fixed. It's not moving as a function of time at the moment of discussion. And inside that you have a density profile. So you have rho as a function of r, and in general rho can be different at different points in r. And if you integrate rho of r over the entire volume dr, dv, r is a vector, dv, then you get the total mass, right? And the total mass um, can change as a function of time, and that could lead to a density difference also, a difference in density. If the mass changes and this surface area, this surface encompassing the volume remains fixed, then the rate of change of density, because mass is flowing out, will be uh, related to the current of mass flowing out through a surface. So in this case, suppose this is a small surface element, ds, right? And the normal is in n hat. And suppose the current, the mass is flowing out, this mass of fluid is flowing out in the j direction, which is different from n, then the current, then the amount of mass being transported will be equal to j dot n, right? So basically you are going to take the I mean, you can take the component of this in the j direction, and that amount of mass is flowing out per unit time, right? And if you write that, essentially, you will get the amount of mass changing as a function of time is equal to the current j dot dA, or in this case ds, right? And if you integrate over the entire surface, that's the total amount of mass which is being exported out of this volume, and that will lead to a density. Now, when you say j dot dA integral over the entire surface area, that can be written by Gauss's law as a divergence of the current. What was the current? J equal to rho into u, right? The local velocity vector. So that is the current. And as a consequence of that, because you're writing down the current J dot dA as a divergence of rho u of the current, integral over dv, and that holds true for any volume, you get your del rho del t plus divergence of rho of u equal to 0. Now it can be shown that if the fluid happens to be incompressible, then the incompressibility of the fluid, that the fluid is incompressible, that leads to a condition of divergence of u equal to 0. So one often expresses that the fluid is incompressible in terms of the fluid flow gradient. Remember, u is velocity field, right? We are saying if the fluid is incompressible, the fluid flow field will be such that its divergence is equal to 0. And why is that? Why do we get that? So just give me a moment to the call. And yeah, so and that can easily be seen by, so you're basically putting this grad and putting it inside the, I mean, you are operating on these two different quantities, as a consequence of which this del rho del t becomes this, and then this is rho divergence of u, and plus u grad of rho. It's operating at part of one of these terms one by one. Now, if you take this term u dot grad rho, right, del rho del t and u dot, and you combine that, that's what is the total derivative. And if you have the total derivative, you can even consider that this element, fluid element, this bigger fluid element, as it is moving as a function of time, it can change shape, right? So basically because there is a flow, the flow field can change this fluid element. So it's the total derivative, the Eulerian derivative, as we discussed earlier, and that we can write as the total derivative ddt of rho, and what remains is rho of divergence u. Now, if the flow was such that density doesn't change, so even if the fluid element changes and flows along and changes in shape and volume, but the density doesn't change, right? So that there's no fluid, I mean, it's incompressible, there's no fluid flow out which goes out of the fluid element, the density doesn't change with time, then del rho del t equal to 0, and then the consequence is, since density is not equal to 0, divergence u equal to 0. Hence, for a fluid flow which is incompressible, where the density doesn't change, the fluid flow will have a characteristic such that divergence u equal to 0, and we use this to discuss or find out fluid flows in the incompressible limit. Like the conservation of mass, we can also have conservation of momentum, especially if there are body forces acting on the fluid. If there are pressure differences, uh, force differences across the fluid, and the direct forces acting on the fluid, then one also needs to write the momentum conservation equation, right? So for the mass was mass inside this volume element was rho dot dv, and the momentum inside this volume element is going to be rho into u. At each point it has a certain momentum, and if you integrate over the entire volume, you will get the total momentum inside this bigger fluid element. But if you have this volume element surrounded by the surface, you could also have momentum transport across the surface. As in before, just first let's assume that this entire surface is not changing as a function of time. It's like fixed surface initially, and you have to look at a momentum transport through the surface, right? And that will actually look at, this is the momentum, and u dot ds is the flux. I mean, this is momentum and momentum flux, and the total flux will be integral over the entire surface. Now let's understand this in a bit more detail. Just look at this curve. Now suppose this was your volume element of the, I mean, right, and this is even a smaller volume element within it, and here it has momentum rho ur, right? This is the momentum field, this is the momentum field. But you also have, you can, suppose this was x direction and this was y direction, you can also say that this smaller fluid element has rho ux, this has a momentum field in the x direction, and rho uy, right? Now suppose this fluid element or some other fluid element here was flowing out through this surface. It was flowing out through this surface, but it has a velocity ur in this direction, similar to this, but I mean some slightly other direction here, right? But the surface is in this direction, right? The normal to the surface is this, and the surface is oriented along this, such that the normal is this. Now you can also ask the question, how much momentum is being transferred along the y direction, call y to be j, right? So then you have to take a dot product of this s or n in the y direction. So that will be essentially ds. This was area ds, n hat dot y. That's the component of the that's the basically uh, I mean the surface area, which is, I mean, if you take a component, I mean, because area is a vector, it has a direction. Along, so this is a smaller area. I mean, I think it's called a projection. It's a projection in the y direction, right? So this is a projection in the y direction. Fluid is flowing, however, out in this direction, right? So this fluid flow has a component, momentum component in this direction as well as in this direction. So you can also ask how much the x component, suppose this is the x component, I, rho ui x component of the momentum is transferred in the j direction, the y direction, like by virtue of uj. Uj means there's a component in this is flowing in this direction, there's a component in this direction, the flow, and you are asking how much x momentum is transferred across this surface in this direction, because the flow was in this direction, right? This ur, that's the question you are asking. Hence now coming back, you have the rho u momentum. How much is it flowing in some particular direction u dot ds, right? That's what you are asking. And if that is the momentum flux, and momentum is a, of course, a vector, so you have three components, you can ask how much total momentum is leaving through s encompassing volume v in time dt, and that is going to be rho u into u dot ds, just as I showed you in the last class, in the last slide. And that is the total amount of momentum lost in volume v. So the total momentum loss, this is the total momentum in volume v, rate of change of momentum in volume v is equal to the flux rho u into u dot ds, right, plus any body force that you might have. And this is integral over the entire surface by Gauss's law. You can get a note. So when you're taking the dot product, the ds in the uj direction, you get uj and j, right? Because you're taking the dot product. So this is the Levi-Civita convention, as a consequence of which you're getting the derivative with in where you have j, right? Because you're taking surface area, you're writing this as derivative of j, and this becomes rho ui uj, because we're taking a divergence of this, right? Plus the force term. Consequence of which is, now this is an integral over v, and this can be written as, I mean, it's a I mean, since it's over the same volume, any arbitrary volume. So here you are writing it in terms of any arbitrary volume, uh, and if you have the equation, the fluid is incompressible, then you know divergence u equal to 0. That's what we showed just before, divergence u equal to 0. And then when you make this act operator operate on these terms, uh, this will give 0, and what you will have is uj del del xj ui. Note, j, there's a repeat over g, which means there's a dot product, right? So when you write this as a dot product, this will be rho del u del t, u dot grad acting on u, and that is equal to the total body force. Of course, there has to be a dv here, right? And since you can have uh, any value of dv, you can write this well. So u dot grad can be written as the total derivative, right? Uh, Especially if it is incompressible. And this is the Euler equation without viscous terms, because we haven't added viscous terms. We have just total body force. And in general, if it's compressible fluid, then you must write rho del u del t plus divergence u u, where this is not a dot product. This is a tensor, right? ui ug. It's a tensor equal to the force, right? This might be a tensor, but we're taking a divergence, right? So it will become finally a vector equation. You will have a del u del t. This is a tensor, but you're taking a derivative, and force is again a vector. And the force in general can have pressure term and other terms, right? And if there is the pressure term, so you're dividing it into pressure, the so suppose this element is surrounded by other fluid, right? And that is giving a pressure to it. So this fluid is giving a pressure in this direction to this element, which is negative, which is opposite to this surface area, right? So the n is pointing outwards. The force due to pressure of the remaining fluid is acting inwards, and hence you have this total force equal to minus p n with a minus sign, because it's acting inwards, to ds, right? And you can integrate over the entire surface area to get the total force due to the pressure. And there can be other terms as well coming from somewhere or the other. Uh, there can be gravity, there could be electric field, and so on and so forth, right? Which is not coming. So the electric, suppose this was charged, or there was gravity, right? So that is not coming due to this rest of the fluid. The effect of the rest of the fluid, the force due to the rest of the fluid, is been incorporated inside P, and these are other terms. And this can be written as, again, converting a surface integral into a volume integral, as minus grad P. Now, if other terms are absent, then you would have in general del u del t plus u dot grad into, and not into u, operating on u. So this is an operator. U dot grad is an operator acting on u, right? Uh, to minus grad p. This is a vector equation. And of course, if you have other forces, the electric field, gravity field, that will act on this. But note, since you're writing it like this, right, it also means that divergence of u equal to 0, it's incompressible. Else you would have to write grad, or rather divergence of u dot u. I mean, like this. Only when the fluid is incompressible, that is divergence of u equal to 0, can you write it in this manner. So what do you have? You have essentially four equations, because this is a vector equation. This is a scalar equation, divergence of u equal to 0. You have four equations, and you have four variables, because you have to solve for u and pressure. U is a vector. So if you have suitable boundary conditions, you can solve for u and p. And that will basically, if you know the boundary conditions, you know the velocity field at every point in space, and pressure field at every point in space. And these are, of course, coupled. Pressure affects u and u affects p. But anyway, you can solve that as a function of space and time, and thereby you have solved the problem. And here we are setting up the broad equation. We are basically writing the momentum conservation equation appropriate for a fluid, but in the inviscid limit, right? The other thing I want you to note is, just 1 second. I want you to know is that we didn't have any energy equation. And the reason we don't have any energy equation when we are looking at this is in the incompressible limit, when volume is constant, I hope this is on. Recording is on, I hope. Yes, it is. Uh, okay, let's mode again. Yeah. So note that there's no energy equation because suppose the fluid was an ideal gas, then you can relate the equation of state P equal to nRT, which is a relation between the pressure, the volume, and the temperature, number of moles. So these are four quantities, and there's a relation between these. P equal to nRT, and if it's incompressible, then the density, the number of particles per volume is constant. The volume of the fluid or fluid element is constant, and then pressure and temperature are directly related. So if you know the pressure, you also and you know the density, you also know the temperature, right? So you don't need an separate essentially energy equation for this system because it was incompressible, right? Of course, you will say that all fluids are not ideal gases, but if they were not ideal gases, you would have a corresponding equation of states. Let's say, suppose the van der Waals equation of state, right? And if the van der Waals equation of state, then again the density would be constant and P would be following T. So you don't need the energy equation because you don't need to solve for density or volume of the fluid. But on the other hand, if you had an incompressible fluid, you would need the energy equation because then you would need to solve rho as a function of x and t, which you don't need to solve now, right? So when we are looking at compressible flows later, there will be a whole 1 or 2 weeks on it. Then we will need the energy equation, but not right now. Now, if there was no external force, this F term, then of course you can write the Euler equation as rho ui del del t del del xj. I have intentionally written like this: ui into uj p delta ij equal to 0, where you have this divergence term, right? And you are looking at the flow of ith component in the jth direction. Note that this is analogous to the conservation of mass, so, where there the current was rho into u, right? But now the current, the momentum current, if you like, is this term, right? So it's a tensor. It's a tensor, but it looks similar, and I want you to note that. Okay. So if you had the fluid in a plastic bag, volume V, right, and the and there was a small hole and all the fluid was flowing out only through this hole, then you could ask how much momentum is changing in this volume, right? And rate of change of momentum is equal to force, right? And so if fluid was flowing out, there would be mass change and also there would be momentum change, and the momentum change would be how much is the force. You can calculate the force, which is uh, which this liquid which this thing is exerting. That would be P1 minus P2 into dA. Remember, this has dimensions of force. That's the amount of momentum which is flowing out. This is the amount of momentum change. So if you know P2, if you know P1 instantaneously as a function of time at a particular instant in time, P1 minus P2 into dA is the total momentum change in this bag in a certain unit of time. Of course, as fluid flows out, this P1 and P2 will change because there will be a pressure drop. Outside, the pressure might be the same. So you have to do P1 minus P2 into d is the force in a unit time, then integrate over it too. Right? So that's the broad idea. Okay, so having an idea of the Euler equation, one can show that one can also derive the Archimedes principle. And for that, just consider that there's some block of maybe wood or some substance which is floating, and put this, choose the axis so that the z line, the z surface is here. So if as and the pressure at on the surface of water or liquid is P0. So and here there is air, and this is of course water or liquid. As you go out, the pressure is decreasing. Uh, P equal to P0 minus rho gz. But as you go in this direction, right? So rho here would be rho of air if you go up, but if you go down, then z would be negative, and P0 plus rho of liquid gz. So this will be then rho of liquid, and pressure is increasing as you go in the z direction, in the negative z direction. This is the negative z, this is the positive z, right? Uh, I don't know. Okay, okay. And what's the force? Rate of change of momentum, we wrote here somewhere. The force was minus grad P, which was the force acting on this fluid, right? Uh, so, yeah. So grad P equal to minus rho G. This is the minus rho G. Basically, the if you are taking this to be an element of the fluid, okay, not wood but fluid itself, yeah, but then basically the external fluid is acting upon this as minus rho g. G is acting in this direction, so there's a force acting in this direction. The fluid is giving a force in this direction. So for a static liquid, if this was an element of liquid and it was static, then minus grad P, it's in static equilibrium, there's no dynamics, there's no time dependence. So in that case, the total force, so minus grad P, which is what is being given on by this liquid on this surrounding liquid on V dash, is minus grad P, and this itself is feeling rho g, the force due to gravity, right? Of course, you can multiply an element of volume and integrate. So grad P equal to rho g. That's what we are getting, the consequence from here. So what we see is that a force minus grad P acts opposite to rho g to keep it in static equilibrium, right? This is feeling rho g, and the rest of the liquid is giving a force on this, which, because we can calculate the pressure, we can calculate grad pressure, and thereby we can figure out how much the remaining fluid is giving force on this. Of course, you have to integrate over the entire surface area. So total force acting is basically minus PdS, right? Because this is the force, and that's on a volume, and you can writing it in a basically surface as a surface integral. So basically, this is, as I said, divergence P integral over dV, and this quantity is minus rho g, yeah, because we showed it here, the dV dash. And if you integrate over the entire volume, that is nothing but the weight of the displaced liquid. So the rest of the liquid is giving a force equal to the weight of the displaced liquid, which is essentially Archimedes principle, right? So what did we use? So here we used this expression minus grad p, and that this is equal to 0. So this is what we use to calculate uh, the force given by the rest of the fluid on this small volume element. Minus grad p integral over volume gives minus rho g. So that's what we used, right? Okay. Uh, Next, we are still looking at consequences of energy equation, and we'll be solving flow fields in the next class. There's something called so in this fluid, and suppose there was a flow field, right? How can we write down the energy conservation equation for the fluid? Okay, for an inviscid flow, we will later write the Bernoulli's equation when there is viscosity, and for that we're going to use the vector identity u cross curl of u, and you can look up your Spiegel or whatever vector calculus books, and it will be this expression. Okay, so this is the expression, just check it up. Now here you see that you have this u dot grad u term. U is any vector, and in our case velocity field. And in the Euler equation you have del t of rho u, and then you have this rho u dot grad u term. That is for only incompressible fluid, and that is equal to minus grad p plus f. This or this you have to replace in terms of this equation. So you take this to the left hand side of the equation, get this to the right hand side of the equation, and what you get is this uh, essentially this is here, this term is here, you see it here, and this term you see it here, equal to minus grad p plus f. Now that's a very extremely cumbersome term, two curls, we don't like curls. On the other hand, we'd like this u dot u, velocity dot velocity, u square, reminds you of kinetic energy, of course, right? So we're going to get rid of this term. And how do we get rid of this term? By doing a dot product with u. Now, if there's a curl of u curl, right? And you do a dot product, by default it is going to be 0, because curl, if you're taking curl, you cross producting something with a vector u, whatever this be, uh, is going to point in the normal direction, right? So if you just take a dot product, this term is going to, so basically that's what I've written, u dot u of anything curled, this quantity is going to be perpendicular, because I've done a cross product before that. Hence this equation becomes, and you have taken a dot product, right? So u dot this can be absorbed into rho u square. Should be very happy. And here again you have u square, and remember the flow is incompressible, right? If it is incompressible, rho you can put it inside, and again you have something like the kinetic energy. You have a grad here, you're putting it here, you are just readjusting the term. What you are doing is taking these and readjusting. There are two places you have u square, so you should be very happy. And this is f dot u, and now f, if it was a conservative force, you can write it as minus grad phi, again a grad, right? So you can play around. So see, there's a u here, you can play around. So what you will get finally, rate of change of kinetic energy across a surface area, a finite volume, is u dot this quantity rho u square, again kinetic energy, pressure, the potential for conservative field, which is giving the external body force, right? uh now 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 this is the kinetic energy, and if you have a steady flow, then along a streamline, At a certain point in space, what you have, so basically along a streamline, is the kinetic energy density. Uh, wait, and this can be written as u dot del u del t, and along a streamline del u steady state del u del t equal to 0, right? Uh, or is it? I think this is the rate of change of u. Yeah, if it's a steady flow, then you won't have that. Right? Del u, if you have a steady flow, then del u del t will be equal to 0. Yes. So this term will be equal to 0. And in that case, you will have, yeah, so if del u del t equal to 0 for a steady flow, holds only for steady flow, then u dot grad h, where h is this quantity, equal to 0. In general, velocity field is not equal to 0, right? And that then grad h has to be 0, which means that h, whatever is there inside this bracket on which gradient was acting, now does not change. What does gradient of a certain quantity be equal to 0 mean? That there is no change along any direction. Sorry, not along any direction, but along a particular direction, along this, along this. So when you're taking a grad and doing a dot product along this streamline, this is equal to constant. So the kinetic energy density, pressure, and the, if you have a conservative potential corresponding to a conservative force field, minus grad phi equal to F, right? How do we use this? To use this, suppose the use of Bernoulli equation in the inviscid limit steady state flow. The assumptions are extremely important. Just don't take an equation, use it anywhere. Also, we used steady state flow, incompressible flow, inviscid. Three conditions. Please remember that. Use of Bernoulli, suppose you had a steady state flow inside a cylinder of area A, right? And the, the fluid flows after that inside a cylinder of a smaller diameter, a smaller cross section, right? And since mass has to be conserved, conserved, the flow of water is fixed, right? So u1 into a1, so the velocity field u1 into a1 equal to u2 into a2, right? So that has to be conserved because there's a steady state, mass of water cannot disappear. And a consequence of that, since you have this relation, you can also write down the Bernoullis, which always is holding true as long it is these three conditions which is said: streamline, steady state, incompressible fluid, inviscid fluid. Then you have this relation. Right? Now u2 and u1, you know the relation. That's related in terms of A, correct? Then you know the pressure drop. Then you automatically know the pressure drop because you can write P1 minus P2 or P2 minus P1, right? And if you know one of these, suppose you know U1, uh, then you know U2, and correspondingly you know the pressure drop, right? Because you have just written, you have rearranged term P1 minus P2 equal to this and minus this, and U2 can of course be written in terms of U1 A1 minus A2, right? And note, P1 minus P2 will be a positive quantity because A1 is greater than A2, right? So here we stop, and then we again start the recording. So where should I stop sharing? Stop recording.